Okay, so what does snake oil and climate change have in common? Well, not much. Snake oil often refers to pseudoscience, where it's advertised in the past to cure all sorts of remedies without any scientific backing. Whereas the Intergovernmental Panel on Climate Change, or IPCC, is a global body full of qualified scientists who agree on human-induced climate change. So the IPCC reports are scientific, whereas the snake oil is non-scientific. And in this course, we want you to be scientists, not pushing snake oil. So, hi, my name is Louise Leonard. I'm an experienced and I'd like to say successful VCE Chemistry teacher, having taught Units 1 to 4 chemistry over the past 16 years. I've also taught IB chemistry. I'm a VCEA exam assessor, so I'll give you lots of tips about what to look for in answering questions. Before I was a teacher, I worked as a food scientist and nutritionist for several large companies in the food industry for about 20 years. And my husband and I also ran an engineering design company. So I've got lots of real-world examples and tidbits to share with you. This is the start of our key science skills, and we're going to look at aims, questions, hypotheses, and predictions. So what's in this lesson? We're looking at developing aims and questions, formulating hypotheses, and making predictions. And we'll come back to these elements right through all the key science skill lessons. Okay, so we're going to start off by looking at the scientific method. And what is that, you might ask? It's a process that scientists follow in a systematic way to make sure that they can test their ideas. It starts off with ideas, observation, curiosity, goes through to making hypotheses and predictions, then performing an experiment, making more observations. Then if the results are consistent with predictions, that contributes to the body of knowledge. But we might find that additional testing does not support the hypothesis, in which case we come back and we revisit the hypothesis and make new predictions. If the results are not consistent with the prediction, we go back and then we rethink again. So it's a process of finding information, connecting it to what we know, and revisiting it. Scientists publish their findings so that they can share them with other scientists. And if the body of knowledge is confirmed, then that observation becomes law and hypothesis becomes a theory. So a scientific idea is a claim that is based on this scientific method, whereas a non-scientific idea like snake oil is not based on this systematic scientific method. Part of the scientific method is using evidence. And evidence can change over time, and that's quite okay in science. The scientific method is based on evidence and is objective. In other words, it can be reviewed by other people to come up with the same idea. On the other hand, personal opinion is what we call subjective, and you might have some subjects like English where you have to write subjectively, but that's not part of science, and it's not part of the scientific method. Also, anecdotes or short stories about persons or events are not considered part of the scientific method. If an anecdote is repeated multiple times and the pattern eventuates, then it can be considered evidence later. And an example is the development of the atom. It's the first idea of the atom, model of the atom, was proposed by John Dalton in 1803, so a couple of 100 years ago, and atoms were seen as solid models of solid spheres. Then 100 years later, this was further developed by J.J. Thomson, Ernest Rutherford, Niels Bohr, and Erwin Schrödinger to find the model of the atom that we consider today, where we have a positively charged nucleus surrounded by clouds of electrons that are moving. And at the time, the evidence pointed to the development of these models and the model of the atom might change in the future depending on what new technology is found. And that's all okay. Okay, this is another map of the scientific method, which shows the steps in a linked circular motion. So we start off with a research question, which is the stage that we're at the moment, at the start of all these key science skills, and problem definition. And then as we get more and more information, we move through the cycle. So we move on to experimental design, collecting data and analysis, evaluating, reporting, and then back to where we begin. So in this lesson, we're focusing on the first two steps. And in other key science skill lessons, we'll focus on the other steps. So the final stage of the investigation is the report, which follows a very specific structure. And we're currently at the title and introduction stages of the report or poster. And through these lessons, we'll go through all of the various stages. Sometimes those scientific reports are communicated as posters, and in Unit 4 Chemistry, you must produce a scientific poster. So in these lessons, we'll show you how you work towards that. So where are we heading? Well, here we have a sample scientific investigation written up as a scientific poster. The poster has particular headings such as introduction, materials, method, a summary of results, discussion, conclusion, and references. And this is a particular style of scientific writing that we're going to show you how to produce. Other types of ways of writing scientifically include scientific reports, infographics, media analysis and responses, and the scientific poster. And your teacher will ask you to present your findings in various ways in SACs. Okay, so in this first phase, we're looking at investigation aims and research questions. And an aim is a purpose for an investigation. It's often written in the following structure: to determine something, or this experiment aims to something. So an aim is a purpose. In the scientific poster that I showed you briefly before, it's what we call our BPA investigation. In that example, the aim, we say this experiment aims to test the effect of temperature on the release of BPA in water. BPA is an organic chemical. A research question summarises the investigation and it ends in a question mark. We have the question mark symbol there. So an example in our BPA investigation, the research question, we could rephrase the aim to make it into a question format. And the question we have, is it dangerous to drink water from a plastic bottle that has been put in a hot environment, ending in a question mark? So the title becomes a summary of what the investigation is about. And we'll revisit this. Okay, the next thing we need to do is identify variables, really important in science. So there are three categories of variables. The IV, which stands for independent variable, is that's changed on purpose by the researcher. The dependent variable is what is observed or measured or calculated, and it changes depending on what the IV or the independent variable is. In order that we can actually see a relationship between the IV and the DV, we want to keep all other variables controlled so that the investigation is what we say is valid. And valid means whether the experiment is designed to test the hypothesis, and also a valid experiment changes only one independent variable at a time. That's another quality of validity. Okay, so let's look at an example. We might have an investigation about the rate of reaction of magnesium ribbon and hydrochloric acid. So the variables we define. So the independent variable, or IV, could be, for example, the concentration of hydrochloric acid. So we might have 1 molar hydrochloric acid, 2 molar, 3 molar, and their variations in concentration. In this case, the dependent variable could be the volume of hydrogen gas that's produced, and that might be used using a gas syringe so that we can measure the volume in a given time using a stopwatch, and that can be used to calculate the rate of reaction. In this case, we want to keep all other variables constant. So we would keep the mass of magnesium ribbon the same, for example, 5 grams. The volume of hydrochloric acid the same, for example, 100 mils. The temperature of hydrochloric acid the same, which would tend to be room temperature, so say something like 25 degrees Celsius. And the size of the reaction vessel. So we might put it in a conical flask that's got a 250 ml volume. So that's one example of an investigation that we could have. Another example would be varying a different variable. So in this case, we might look at the temperature of hydrochloric acid. So we might look at 4 degrees Celsius, 16 degrees Celsius, 25 degrees Celsius, and 50 degrees Celsius. But we want to keep everything else constant. We're still, in this case, still collecting the hydrogen using a gas syringe and looking at the volume of hydrogen that we collect in a given time to calculate the rate of reaction. We want to keep the mass of magnesium the same, so still say 5 grams. We want to keep the volume of hydrochloric acid the same, so 100 ml. But this time we want to keep the concentration constant. We varied that in the last experiment. This time we want to keep it constant, so maybe 1 molar hydrochloric acid. And again, we keep the size of the reaction vessel constant. By doing this, we can control the experiment, and so that we can actually test if we change the independent variable, whether it has a direct effect on the dependent variable. Okay, in our BPA investigation, the independent variable is the temperature that the water is stored at in the container. So temperature, and a second independent variable that's a different set of experiments, whether the bottle, the plastic bottle, contains the chemical BPA or not. So 2 sets of experiments. The dependent variable is the absorbance or area under a peak at a particular retention time using the technique of HPLC, which we'll look at later in the course. And it's also the process data of the concentration of the BPA in the water. The controlled variables are everything else. So we're using the same HPLC instrument for all the trials. We're using the same calibration curve, the same volume of water that's stored in the bottles, and the same environmental conditions to store in the temperature environments. So all bottles are stored at 4 degrees Celsius and the same conditions, or 25 degrees Celsius, for example. The next thing we want to do is formulate hypotheses. A hypothesis is a prediction about what the researcher expects to find in an investigation. And there's normally a structure to writing this. We can say if, and then some sort of phrase that outlines the relationship between the dependent variable and the independent variable. If something is affected by, then, so it's an if something then there's an effect on the trend indicating the effect on the dependent variable. For example, there could be an increase or a decrease, some sort of change. And then the next part is if, then, when. We can say that the trend indicating the action of the independent variable. It might be increased or decreased or greater or less than. So if we go back to our idea of the magnesium hydrochloric acid experiment, we could write the hypothesis this way. If the rate of reaction is affected by the concentration of reactants, then the rate of reaction of hydrochloric acid with magnesium will increase, our prediction, when the concentration of the hydrochloric acid increases. So as one goes up, the other goes up. And it doesn't matter if the hypothesis is not shown to be correct. The main thing is to make a prediction based on what you know at the time. So in our BPA investigation, our hypothesis could be it's expected that if the breakdown of BPA from plastic depends on temperature of the surrounding environment, so the temperature that the water in the plastic bottle is stored, then an increase in temperature would result in an increase in the concentration of BPA that's found in the water. Okay, so predicting possible outcomes. I'm sure that you've looked at either the Bureau of Meteorology website or watched the weather forecast, and we see what predictions, what the Bureau of Meteorology is predicting will happen to our weather over a few days. So it's what the investigator expects to happen. But predictions can be wrong. And that's the beauty of science. It's about the method, not whether the prediction is right or wrong. So whether it's going to be 17 degrees in Melbourne tomorrow, might be 17, might not be 17. So an example, if we look at our experiment where we're looking at the effect of temperature on the rate of reaction between magnesium and hydrochloric acid, a student might expect that the temperature of reactants does not affect the rate. However, if the results show that the temperature does affect the rate, then we can say that the hypothesis was not supported. So we never say a hypothesis is proved or disproved. We say a hypothesis is supported or refuted, where refuted means not supported. So for an example, in our BPA investigation, it's expected that if the breakdown of BPA from plastic depends on the temperature of the surrounding environment, so the storage conditions, then increasing the temperature would result in an increase in the concentration of the BPA chemical found in the drinking water. Okay, so where we're heading is to try and build a scientific poster. This is our BPA experiment. BPA stands for bisphenol A, a monomer or a small building block of plastic, which there are health concerns about. So at the moment we are looking at the introduction section of this poster, developing aims, hypotheses and research questions. And throughout these lessons we will come back and actually work out how to pull it all together. Okay, so another question for you. If we know that density is a measure of the mass of a substance in a given volume, and density has this relationship, it's mass divided by volume, then Mitchell measured the mass of different metals and he used a displacement can, which is this bit of equipment here, to determine the volume of each sample. So we put the metal into the can, it displaced water, which came down into the measuring cylinder, and he could measure the volume of water that had been displaced. The question is to identify the aim, the IV and the DV for the investigation. Have a go at that question. Okay, so we're looking for the aim, the IV, the independent variable, and the DV, the dependent variable. So the aim is to determine the density of various metals, that's correct. The independent variable is the type of metal. So example, if it's iron, copper or zinc, so that is what was changed on purpose. And the dependent variables are the things that are observed or measured or calculated, and that is the mass of each sample. We'd like to know how much mass is in each, the volume displaced, and then the calculated density in grams per mil. So they're all correct. Let's have a look and see why the other options are incorrect. The aim here to determine the density of various metals, that's the same as what we had, so that's correct. But B is incorrect because it says if the type of metal changes, the density of the material will also change. That's a hypothesis. They're not aims. The independent variable is what is changed deliberately by the researcher, and that was the type of metal. The mass of each sample, the volume displaced, and the calculated density in grams per mil, that's describing the dependent variable, not the independent variable. Silver will be the most dense is a hypothesis, and the weighing balance used is just a piece of equipment or a controlled variable. The type of metal is not the dependent variable, it was the independent variable. Determine the density of each metal sample is an aim, so that's not a dependent variable. The same displacement can will be used throughout the experiment, that's a controlled variable, so our answer is D. Okay, so to summarise, the scientific method involves a systematic approach with key steps in order to undertake an investigation. A research question tells the reader what to expect in an investigation and it ends in a question mark. An aim outlines the purpose and can be written in as something like to determine. A hypothesis is a prediction of what the researcher expects to find. The variables need to be clearly defined, so the independent variable or the IV is what is changed by the researcher. The dependent variable or the DV is what is observed, measured or calculated by the researcher. And all other variables are kept constant, which means they are controlled variables. And we've been looking at steps 1 and 2 of the process. So next up is planning and conducting investigations, part 1. See you soon. Bye.